Okay, so far in this series, we've encountered a lot of ideas. We've encountered the ideas of categories and functors and products and the notion of taking the product to two categories. And what we're going to do today is to reap the rewards. We're going to explore the connections between these topics, and that's really going to come together when we look at the product as a functor. Okay, so this gives us a much deeper appreciation for what this notion of the categorical product really means. And we're also going to do something else, which is essentially going to double the amount of insights that we get without any extra work. And that's simply to realize that every category has a kind of dual called its opposite category that's just obtained by reversing all the directions of the arrows. So what that means is that almost every time which we make up some concept in category theory and we work out some implications of it, we then get another big idea for free just by thinking about the same situation with the arrows reversed. So we're going to do that for the notion of a terminal object, and that's going to give us the important idea of an initial object. But the most useful thing perhaps that we're going to do is to look at this idea of product and the different things which we've learnt about it, and then we're just going to generalize them. So we're just going to say, well, what about if we're doing the same kind of constructions in the opposite category? And that's going to give us the notion of the coproduct of two objects. Now, coproduct, I would say, is equally important to the notion of product. And between the two of them, we can construct lots and lots of very useful data structures. Okay, so now I want to talk about duality. So basically, there's this idea in category theory, which is, on one hand, seems quite basic, but on the other hand, it's very powerful because it sort of doubles how much stuff you get out of the theory. And that's just the idea that if you have a category, you can just reverse the directions of all of the arrows and you get another category. So this means there's a natural sort of duality in category theory. And when you define some kind of an object, or often when you prove some sort of a result, you can then sort of for free, you can just say, well, there's another corresponding construction when all the arrows are reversed. So often when you do reverse the arrows in a construction, you get something which has quite different properties. So it can be quite surprising how much economy you get out of this idea. So one of the simple things that we've talked about is this idea of a terminal object, for example. And remember that a terminal object has this property that, well, it's defined by this property that for any object, there's just going to be one arrow into the terminal object. So we can then say, well, what is the dual of this concept? And so the dual idea that we shall call an initial object, we can say an initial object is a terminal object in the opposite category. So remember, this opposite category is this category where we reverse the directions of all of the arrows. So if you have a category and then you take it and then you get the opposite category, so you reverse the arrows, and then if you find a terminal object in there, then you can say, well, what does this correspond to? It corresponds to an initial object. And I think it's fairly straightforward to see what this is going to be. It's going to look like this. There's our initial object. So let's write down a more direct definition of what this initial object is. So an initial object is defined by the feature that for any object there's just going to be one arrow from the initial object to it. And that includes itself, okay? So this single identity arrow that it has is going to be the only arrow from itself to itself. Okay, so at the moment we're just doubling definitions, but there's quite a lot more that you get out of this notion of duality, okay? In general, if we have a category C, then the category that we get by reversing all the arrows in C is often denoted as C-op for opposite. So we can ask, I mean, we have this notion of an initial object now. We can ask about the category set. I mean, we identified a terminal object in the category set. That will be a singleton set with just one element. And we can then ask, well, what is a initial object in the category set? And it's a very good question to think about. It's actually quite weird, the idea of an initial object in the category set. There is one, but it's maybe quite hard to guess what it would be. Okay, so we have this conundrum then. We have the category set that has these objects representing sets and these arrows representing functions. And we want to know, what is an initial object in this category set? And the answer is the empty set, okay? So this is perhaps peculiar if it's the first time you've seen this kind of thing. I mean, maybe the empty set didn't cross your mind. This empty set, this is the set that doesn't have any elements. And it's very important in set theory. For example, the empty set is contained within every other set. It has very important properties, much like 0 does in arithmetic. And so how can we see that the empty set is an initial object in this category set? Well, if that's true, then there must be a function from the empty set to any other set. That seems a bit strange, doesn't it? How can there be a function from something that doesn't have any elements? Well, there's different views that you can take on this. One is that this function would be a sort of bluff. I mean, I tell you that I have a function from the empty set to this set here with A and B. And you say, really? And I say, yeah, you give me an element of the empty set and I'll give you an element of this. And you can't give me an element of the empty set. So there is a function from the empty set to this one. And why is, okay, so if you buy that, then maybe you'd say, well, okay, well, why isn't there more than one? The reason that there isn't more than one function from the empty set to this set is that we define two functions to be the same when they have the same source set and the same destination set, and they're equal for every argument. And any of these kind of null kind of functions from here to here would be the same. They'd all just not have any inputs and not have any outputs. So there's exactly one from here to here. Maybe even stranger is that there's a function from the empty set to the empty set. But again, we just say, well, you give me an element of the empty set and as an input, and I'll give you a member of the empty set as an output. But I mean, that is a little bit strange, because if we have any other set, a non-empty set, then clearly there are no functions from that into this empty set. because if you have an element in here, how can you send it to an element of the empty set when there aren't any? Okay. But, you know, this peculiar kind of reasoning does seem to make a bit of sense. And perhaps a easier way to get your head around this idea is to take an alternative view about what a function is. Okay, so here we have a function, and this is the sort of standard view. It's something that you take an element of this set on the left and you get an element of this set on the right. Another way to think of what a function is that the function is itself a set of pairs. And these pairs, well, the first entry in the pair comes from the source set, and the second entry in the pair comes from the target set. And every element of the source set appears in exactly one pair, and it's paired with the thing that it gets sent to under the function. So, I mean, this makes a lot of sense. We're essentially just making a sort of something like a sort of table, except the order of the entries don't matter, but we're making a sort of table of all of the outputs that this function would have for all the different inputs, and clearly that's representing all the relevant data. And this is often how mathematicians define functions, and in this kind of view it makes a bit more sense, because you could say, well, if that's what you mean by a function, if we just have to have all of the members of the source set appear once paired with some member of the destination set, then a function from the empty set is just a sort of empty thing like this. It doesn't have to have any entries in here because there aren't any entries in here. So a sort of empty object like this would be describing a function, say, from here to here. I mean, obviously that would also be an empty set. In this kind of view, the function from an empty set to some other set would be described by an empty set of input element, output element pairs. So hopefully this convinces you that yes, the empty set is in fact an initial object of this category set. And when later we see connections between what's going on in set theory and what's going on in logic, this gets quite interesting. But I'll leave that for another time. Okay, so I've been claiming that this notion of duality is a very powerful one, but so far all I've got out of it is this idea of an initial object as the sort of dual notion of a terminal object. And you might say, well, I could have come up with the definition of an initial object on my own. It's not really such a great jump forwards. But what we're going to do now is ask ourselves, what's the dual notion of a product? And we've already seen that the product is a very powerful concept, and we're going to get an equally powerful kind of idea by thinking about what the dual of this notion is. And that's called the coproduct of a pair of objects. So now you know what a product is, I can tell you a very succinct definition of what a coproduct of a pair of objects is. And essentially, the coproduct of a pair of objects is just going to be their product in the opposite category. So, say you have a pair of objects and you're interested in determining the coproduct of them. Well, if you go to the opposite category by reversing the directions of the arrows, if you're able to find the product of these objects, so that's going to be something with an arrow into each, which satisfies special properties, then you can take that and then just go back into the original category. So you reverse these arrows, And now these three things, the arrows into the thing and the object, constitute the coproduct of these two objects. So these are dual notions. And so to really get a sort of full description of what the coproduct is, we just take this description and sort of dualize it, reversing the directions in our explanatory diagram and so on. So here we have again the definition of a product. Recall that it's an object A times B with an arrow pi1 into A and an arrow pi2 into B that has the property that for any other object with arrows into A and into B, there's a unique intermediary arrow from that object into our product that makes this diagram commute, in the sense that if we compose it with pi1, we get our arrow F into A, and if we compose it with pi2, we get our arrow G into B. Oh, and I should also say that I'm drawing this H arrow dotted to represent that it's the unique arrow that makes this diagram commute. Okay, so now to get this idea of a coproduct, the coproduct of a pair of objects in a category is just the product in the opposite category. So what we're going to do is just to reverse all the directions of the arrows in this picture. So we're going to denote this coproduct as A plus B instead of A times B. So this is going to be our diagram which defines what the coproduct of a pair of objects is. So I'll simply write down the definition. I've basically just redrawn this diagram here, but I've reversed the directions of the arrows. And now I'm calling these arrows here P1 and P2, whereas I called them pi1 and pi2 over here. And so here we have the definition of the coproduct. So just like we had the notion of a candidate product being something that had arrows into A and arrows into B, we can similarly say that a candidate coproduct is something that has arrows into it from A and from B. So then the coproduct of A and B, which we write as A plus B, has an arrow P1 into it from A and an arrow P2 into it from B. And it has the property that for any other candidate coproduct, like this one X, there it is with its arrows into it F from A and an arrow into it G from B. Well, for any candidate coproduct, there's going to be a unique intermediary arrow H, this time from the coproduct into this candidate X, which has the property that it makes this diagram commute. Okay, so it's such that for any other candidate X with its arrows from A to X and B to X, there's going to be a unique H from our actual coproduct into the candidate, which has the property that H after P1 is equal to F, and H after P2 is equal to G. Okay, So hopefully you can convince yourself that if something is the product of a pair of objects within a category C, then it's going to be the co-product of those objects within the category C op that we obtain by reversing all the directions of the arrows in the category. And conversely, of course, if something is the co-product in a category C, then it's going to be the product in the opposite category. So these are dual notions to each other, and they have roughly equal importance in mathematics. So we're going to now think about what the co-product would mean in this category set. I mean, it's not always the case that you can determine the co-product of a pair of objects. There may not, for example, be any arrows from the pair of objects you're interested in into a particular other object. There may not be any candidates. But in many cases you can determine the co-product. There are cases where you can determine the product of objects, but you can't determine the co-product of objects. But in this category set, it's nice enough that not only can we determine the product of any pair of objects, we can also determine the co-product of any pair of objects. So let's discuss how we can do that. Okay, so let's discuss what this notion of co-product means in this category set. So I just want to go over something pretty basic in set theory that you probably all already know, but I don't want to assume any prior knowledge, so I'm going to tell you anyway, which is what the union of two sets is. So the union of a set A and a set B is usually written as A cup B, and this is the set which just has all the elements which are either in A or in B. So is it true that the number of elements in the union is equal to the number of elements in A plus the number of elements in B? Well, no, not always, because for example in this case we have that 3 is an element of both of these, and so it's only going to appear once in the union. Okay, because sets have the property that they can only have one copy of any particular element. So often we would write a set using curly brackets because it's easier for linear text, of course. So this would also denote the set A. And so now let me tell you what the co-product is. And we can write it as A Cartesian producted with the singleton set just containing 0, union B Cartesian producted with the singleton set containing 1. Okay, so this is, or we can think of this as what the co-product of a pair of objects A and B is in this category set. Now, just like the product had the property that any two things satisfying the product are isomorphic to each other, the co-product also has this property. So it doesn't exactly matter what we tag our sets with as long as we don't tag them with the same thing. So what does this look like? Well, essentially what we'd be saying is that this set here, A times the singleton set with 0 in, it looks like 1, 0, 2, 0, 3, 0, and if we union this, with this thing here, (3, 1, 4, 1, 5, 1, well then we do get something with 6 elements, because there may be 2 copies of 3 here, but they're tagged differently. This one's tagged with a 0 and this one's tagged with a 1. So this is the coproduct, or at least it can be thought of as representing the coproduct of A and B. So we're using a little bit of sophistication here in a way, because firstly we're sort of taking it for granted that if we form these pairs here just by appending a 0 onto the end of every element like this, then we're getting a set which is isomorphic. So this is actually, this idea itself is actually quite deep, because it too can be formalized in terms of category theory. I think it's true in general that if you have a category where the product of any pair of objects is defined, and that category has a terminal object, remember the singleton set is a terminal object, well, I think it's always true in such a case that when we take the categorical product of an object with this terminal object, we get something that's isomorphic to the original object. So you might want to try and convince yourself of that. But that doesn't really matter in this context, because I'm just talking about the category set, and we can see more clearly that it's true in the category set where we're doing the Cartesian product. It's obviously true that if we take the Cartesian product of a set with a singleton set, we're just going to get an isomorphic set. I mean, this set basically looks the same as this one. It's just that we've clipped these zeros onto the end of all of our elements. I mean, actually defining the union of 2 sets is a bit more tricky in terms of category theory. Really, this notion of the coproduct, this sort of discriminated union, is in a way a lot more basic. Okay, I mean, think about it in computational terms. If you want to take the union of 2 sets, you have to go through quite a bit of effort to establish whether they have any common elements, and if so, which. Whereas to take this sort of coproduct, this sort of discriminated union, you simply have to get all the elements in A and tag them with something, get all the elements in B and tag them with something else, and then just stick those 2 sets together. And so this can be thought of as what the coproduct looks like in the category sets, although it doesn't really matter what you tag things with. I mean, essentially coproducts is this kind of thing which is just defined up to isomorphism. Anything isomorphic to this type of form can also be considered to be a coproduct of those sets. Okay, so I want to illustrate how this notion of coproduct works in the category of sets. So what we're going to do is have a look at how we're going to have a look at the coproduct of this set A and this set B. So here's this sort of categorical picture of what's going on. Now, the first thing we need for this thing here to be a coproduct is we need it to have a we need there to be an arrow from A into it and an arrow from B into it. So I'm calling those P1 and P2. And remember when we were doing products, we were calling the arrows projections. Well, it would probably be good to call these arrows injections, because essentially they're just going to inject elements from these sets into the place where they are floating around tagged within A plus B. So 1 is going to go to 1, 0, 2 is going to go to 2, 0 under P1, and U is going to go to U1 under P2. So these are the special kind of injections which come with A plus B. And now I have to try and demonstrate to you that this is a coproduct, okay? So this coproduct comes with these injections here, and we have to show that for any other candidate coproduct, say X, say for example we have something with elements R and S, well, let's say that this is a candidate coproduct. So then there must be some arrows, some functions from A to X and from B to X. So let's just make one up. So we've just made up a function f from A into X and g from B into X. So now, in order for this to really be a coproduct, we must have that for any other candidate like this, there's a unique arrow. So I'll draw it dotted because it's unique. It's unique with respect to the property that it makes this diagram commute, okay? So we want that if we do this injection and then we apply H, we get, if we do this injection P1 and then we apply H, those give us F as a composition. And similarly, if we do the P2 projection and then apply H, we get the same thing as if we just applied G. So how can we make such an injection from A plus B into X? Well, I propose we try H of X comma Y is equal to f of X if Y equals 0 and G of X if Y equals 1. So remember, the elements in this set A plus B here are tagged, so the ones that came from A are tagged with a 0 and the ones that came from B are tagged with a 1. So this kind of, what I'm proposing for this intermediary arrow, it'll have a look at 1 comma 0, it'll say, okay, your last entry is a 0, I know you came from A, so I'm going to apply F to you. I'm going to apply F to your first entry. Similarly, this came from A, so I'll apply F to the first entry. and this one ends with a 1, so we're going to apply G to its first entry. So now hopefully you can see that that H makes this diagram commute in the sense that F equals H after P1 and G equals H after P2. And that's what we want. But recall that in order for this to be a coproduct, we also need that this is the only such H that makes this commute. So is that clear? Well, suppose we had an element xy in here, and let's suppose, without loss of generality, that y was 0. Okay, so we'll suppose that it came from this set A. Well, then we better apply F to its first entry. If we sent this element x comma 0 to something different than f of x, well then it wouldn't match up, because it's getting sent to, so x gets sent to x comma 0 under P1, and then it gets sent wherever we send it to H, better be f of x. So we really have to specify our intermediate kind of function H here like this. Nothing else will do. So indeed there is just one intermediary arrow given any other candidate coproduct, which makes this diagram commute. So indeed this is going to be a categorical coproduct. Okay, I just want to make sure the terminology is clear again. So I suppose in set theory terms this should be called a discriminated union. So I've just tried to show you that a discriminated union with the injections associated corresponds to a coproduct. Okay, and just like in the case with products, any two coproducts are going to be isomorphic to each other. So that kind of shows you the converse, because if something is a coproduct, well then it must be isomorphic to this kind of discriminated union. Okay, so now we know about this duality and these relationships with coproducts. There's even more reason for us to be interested in what are the properties of products, because we now see that whatever we learn about products we can sort of generalize to coproducts as well, in some sense. Now what I want to do next is to connect together a few of the things that we've been learning about. So basically I want to relate the idea of products with the idea of functors. I want to show that in some sense the categorical product can be viewed as a functor. And to do this we're going to have a look firstly at some fairly simple example in set, and then we're going to build up in generality until we get a view of a product, a general categorical product as a functor. And this is going to be very useful because, for example, we already have a notion of what it means to multiply two objects together in a category, but we're also going to get a notion of what it means in some sense to multiply two arrows together in a category, because when we're dealing with functors we have to know how they map objects and how they map arrows. Okay then, so let's have a look in this category of sets at how we can view product as a functor. Okay, so we're going to start in this category of sets, and we're going to do a functor from this category of sets back into itself. Right, so I've just drawn two copies of it because that's easier to visualize. And basically what we have, all these sets, and we have different functions between them, and we want to sort of lift all those goings on into a new setting where all of those sets that we're playing around with have all been Cartesian producted with this W. This is another set. So just to put this into a bit more practical terms, let's say that you had a list of people's names, and next to their name you had, let's say, the GPS coordinates of their home, okay? And then you made some function which takes in a GPS coordinate of someone's home and outputs, say, the distance that they are from your location, okay? So maybe then you'd want to apply that function to everybody's information. So you'd start off by taking in this GPS coordinates and name, and then you'd want to do some function of the GPS coordinates. Let's say that calculates how far they are away or something, and you want to keep the name. Right, so if you wanted to do that kind of thing, you'd essentially want to sort of lift this function so that it was being applied to, it wouldn't just be mapping A to B. You'd want to map A times the set of words for set of names, well, including the set of names, to B times W. And here this is the Cartesian product. Okay, so we're just talking about pairs. So how can we think of this in the context of category theory? Well, what we can do is we can make a functor which goes from set to set, and it's going to send an object, a set, to the Cartesian product of that set with this set W. So each one of these sets gets sent to a set times W. Now remember, this is not a function on these sets. It's not, this functor is not sending, it's not telling us how every element in here is getting sent to an element in here. It's just something which takes a set and sort of points it towards this other set here, A times W. And so that's how this functor operates on objects. But to define a functor, we have to say how it operates on objects and also how it operates on arrows. So we have an arrow like this, a function, and it's a function from A to B. And when we apply this functor, it's going to change into a function from A times W to B times W. And in this case, it's defined like this. So it takes in and inputs a member of this set, little a comma W, a pair, and it just applies this function to the first member of the pair and leaves the second member unaltered. So it takes A comma W to F of A comma W. Okay, so how do we know that this way of sending category set to category set is actually a functor? Well, it has to satisfy the two laws of a functor. And that is basically that the image of the composition of a couple of functors ought to be the composition of their images, and also the functor should send the identity arrow to the identity arrow. So I've tried to demonstrate this here, and basically the idea is just that we look at how this, because these are functions in this case, right? They're functions over here and they're functions over here. So to prove that two functions do the same thing, you just look at how they work on a sort of general element, and if they map that general element in the same way, then they're the same function. Okay, so for example, to prove this one, we can just look at how these functions work when we feed in a element a comma w, and we see that we get the same results in each case. And similarly, you can show that this law holds by thinking about how these things work on a general element. I'm not going to talk through this. You can pause the video and have a look at this. Okay, so we're going to need this idea of the product of two categories, C and D. So I wanted to remind you about the definition of this. So this product here is going to be a category, and it's going to have objects A comma A bar. Whenever A is an object of C and A bar is an object of D. And this category is also going to have arrows, and the arrows are written F comma F bar. Now that's going to be an arrow from A comma A bar to B comma B bar whenever F is an arrow from A to B in C, and F bar is an arrow from A bar to B bar in D. So now we know what the objects of this category are. They're essentially just the Cartesian product of the arrows in C and the arrows in D. And we also know what the arrows of this product are. The final thing we need to know is how to compose these arrows together. And the basic rule is that the composition of a pair is the pair of the compositions, okay? So if we want to compose G comma G bar with F comma F bar, then the result is G after F, comma G bar after F bar. So to work out this composition, we just take the first components in the pair and compose them in C, and take the second components in the pair and compose them in D, and then just pair those results together. Okay, so what we've done so far is to show that the Cartesian product can be viewed as a functor, in the sense that if you have some fixed set W, then you can say, well, if I get other sets and multiply them by those, I can think of those as the objects that this functor sends those sets to. And the arrows in sets, the functions, also have images under that functor, which are going to be functions from sets like A times W to B times W. So in that case, we were holding this set W fixed. Now, one gets a more general viewpoint if one allows that second set to vary as well, because then you've got a type of something like a sort of functor in two directions, if you like. But this can all be formalized using this idea of the product of categories. So set is a category. It has these objects as sets and these arrows as functions, and we can consider the product of the category set with itself. So this is this notion of products of categories. Okay, so the result is going to be called set times set, and if you recall from the definition of a product of categories, the objects in this thing, set times set, are going to be pairs. An object from this category and an object from this category. Categories are the same, so the objects are going to be pairs of sets. And the arrows are going to be pairs of arrows, an arrow from this category and an arrow from this category. So we'd have an arrow f comma f bar, which takes us from the object a comma a bar to the object b comma b bar. Okay, so this category is not a load of sets, it's a load of these objects which are sort of abstractly representing pairs of sets. But remember the way we compose arrows in this product of categories. We'd have that g comma g bar after f comma f bar is g after f comma g bar after f bar. Okay, so that's the critical way we compose arrows in this product of categories. Now, to get this bigger view of this product operation as a functor in two directions, we're going to consider it to be a functor from set times set to set. Okay, so what it's going to do is it's going to translate an object in set times set, like a comma a bar, and it's going to send that to the Cartesian product of those sets. So a comma a bar is going to get sent to a times a bar, similarly with the b's. And what happens to this arrow here? Well, this arrow is going to get changed into a function which goes from a times a bar to b times b bar, and we call that function f times f bar. Now, the way this function works is that when it's operating on some element a comma a bar, we're just going to operate using these two functions f and f bar on the two pairs, or on the two elements of the pair. So we'll just do f on the little a, and we'll do f bar on the little a bar. So the result's going to be f of a and f bar of a bar paired together. And that's going to be an element in this set here. Okay, so here's the sort of algebraic description of what's going on in this picture up here. We're saying that f is a functor. It goes from the product of the category set with the category set to the category set. It sends a object, which is a pair a comma a bar over here, to the Cartesian product of a and a bar. And how does this work on an arrow of this category? Well, if we have an arrow f comma f bar from a comma a bar to b comma b bar, that's an arrow over here, its image under this functor is going to be f times f bar, which is defined like this. So it's a great exercise to convince yourself that this is a functor. Okay, it's just a few algebraic manipulations, and you can show that this satisfies these two laws of a functor, that the composition of images is the image of the compositions, and that it maps identity arrows to identity arrows. Okay, so now I'm going to explain how to do what we just did for set, but for general categories. Okay, so what I just did for sets was to say that there's a sort of functor which goes in two directions, if you like, which basically works with this notion of product. And I'm going to do the same thing for a general category C for the categorical product. Now we're going to suppose that we're lucky enough that this category C is such that for any pair of objects we can find a categorical product. Recall that the categorical product of a pair of objects A and B is another object which we call A times B, together with some arrows, one called pi1 which goes to A and one called pi2 which goes to B. We often call those arrows projections, and it has the property that for any other object which has arrow y which has arrows into A and into B, there exists a unique arrow which has the property that this diagram commutes. So going along H and then going along pi1, their composition is equal to P, and going along H and then going along pi2, their composition is equal to Q. Okay, so we're going to suppose that there is a product like that for any pair of objects, and in that case we have this kind of functor which is very similar to the kind of functor we looked at with set. I mean, remember that one with set, it went from the product of the category sets with itself back into set. This one is a functor from the product of C with the product of C. This is a product of categories. It goes from that to the category C. So here's a picture of it. I haven't drawn the identity arrows, and we have some objects and arrows in C, and then another copy of C. We take the product of these two categories and we get this category here, which is C times C. It has objects which are pairs of objects from C, and it has arrows which are pairs of arrows from C. And we're going to define this functor, which is basically the product, the categorical product. So we're going to associate every object over here, an object of this category, which is a pair, we're going to associate that with the categorical product of the, well, a categorical product of the two things in that pair. Okay, so we can say, okay, we've got A and A bar, and we can just do this kind of construction here. So we can just take A and A bar and then say, okay, well, I can find an object which I'll call A times A bar, which has this property that you know, has these projections into A and into A bar, and it has this property that for any other objects Y, which also has arrows into A and A bar, we can find this unique intermediary arrow that makes this diagram commute. Okay, so we'll do that for every object in this category C times C. So there's one for A comma A bar, there's one for B comma B bar. And the other thing we have to do, since we're trying to make a functor, we've said how to send objects to objects, but we also have to send arrows to arrows. So I'm saying that this pair of arrows, F comma F bar, gets sent to this thing here, f times f bar. And I haven't told you what that is. I'm going to go through the definition now. It's a very lovely definition, I think. So the way it works is we have a times a bar over here, and we know it has these projections, pi 1 and pi 2, which go into A and A bar. We also have this thing here, which has a similar type of nature. Well, what else do we know? Well, we know that we have this arrow F, which goes from A to B. I mean, we're trying to, we're saying we're starting with F and F bar, and we want to somehow construct this thing that we can think of as the product of those arrows. So we have our F, and we also have our F bar, which goes from arrow A bar to arrow B bar. Now here is the clever bits. If we compose this arrow and this arrow, we get an arrow from A times A bar so this arrow here is just going to be F bar after pi 2. We also can do the same thing over here. And we get F after pi 1. So now what we can do is look at things from the perspective of B times B bar and think of this as a candidate for being a product. And we'll think, well, hey, you're a candidate. You have these arrows going into my B bar, so I can do what you can do better. That means there's going to be a unique intermediary arrow from this candidate to this, which is going to be like this, which has the property that going along here and here as a composition gives us this, and going along here and here as a composition gives us this. And that's what we call F times F bar. It's this unique arrow. So that's the definition of F times F bar. It's the intermediary arrow from A times A bar to B times B bar, and it's unique, so we have a proper definition of it. And how do we compose these type of arrows? Well, I think it's very natural. So you can say we have another thing G times G bar going to C times C bar. Well, we just extend this picture. So we just go, okay, we go along G to get C. We can go along G bar to get C bar. There's going to be a product of these two. Remember, we're assuming that there is a product for every pair of objects. We have pi 1 squiggle squiggle and pi 2 squiggle squiggle. And again, by the same type of logic, Well, here, let's draw it in. If we go along here and here, we get an arrow like this. If we go along here and here, we get an arrow like this. So there's G times G bar, and we simply compose these arrows. That's all we have to do. That's going to be, composing these arrows is straightforward. Okay then, so this really brings together a lot of the things we've been talking about today. We have the idea of categorical products of objects, so we know that now, which is very useful for us. Now we also have this idea of the categorical product of arrows, and they're both involved in this as a functor. And so I think it's a great exercise to try to bring these things together to show that this is actually a functor. So we need that the composition, we need that the image of the composition is equal to the composition of the images of arrows. And you can show that by looking at this picture here. And then the other thing you want to show is that this functor sends identity arrows over here to identity arrows over here. Okay, so now we have this kind of deeper understanding of what a product is in terms of functors. We can, of course, exploit this notion of duality. We can basically dualize a lot of the things we've learned and apply them to coproducts. So coproducts can also be viewed as functors.